Hello, my name is Francis Kataki. I'm with Challenge 2017, and today I'll be talking to you about derivatives. Now, a derivative is basically a slope. However, the difference between a slope the slope that you normally hear discussed in algebra classes and the derivative is that the derivative represents an instantaneous rate of change. Now, what do I mean by that? On the highway, when you see police officers with their radar guns trying to track the cars that are going over the speed limit, um, the gun, it actually captures the the instantaneous rate of change of the cars. That is to say, the speed at that instant, not their average speed that they travel, I don't know, for about 10 minutes, 15 an hour. But in this case, a derivative is just the instantaneous rate of change as opposed to the average rate of change. Now, how would we represent that on a graph? Here, let me draw it out for you. Okay, so I'm going to have this curve, and let's draw a line here. I'm going to denote this point as x, f of x, and this one as x plus delta x, f of x plus delta x. Now, using the definition of the slope that we're familiar with, which is to say delta y over delta x, we're going to find the change in y divided by the change in x. So that'll be f of x plus delta x minus f of x divided by the change in x plus delta x minus x. And these two x's will cancel out here in the denominator, leaving us with f of x plus delta x. F of x plus delta x minus f of x divided by delta x. Now, we're closer to our what we want, which is to say the formal definition of the derivative. However, we have not arrived there yet. This line is a secant line, which is the average rate of change. We want the instantaneous rate of change. That is to say, the slope of the tangent line, which is a line that intersects a graph at one distinct point. Now, for the derivative, the formal definition, I'm going to add some fancy notation here. Allow me to explain. So here we have the limit of f of x plus delta x minus f of x divided by delta x as delta x approaches 0. Meaning that if we were to find the average rate of change of points that were closer to this point, we would get closer to this point's rate of change. So let me give you an example. We're going to use a function x squared. So that's basically a parabola. Now, using the formal definition that I just presented you with, delta x, so f of x divided by delta x, we're going to plug this into x squared, which will give us x squared plus 2 delta x minus x squared, all divided by delta x. Excuse me, I'm sorry. I forgot the x squared here. So this will read x squared plus 2 delta x plus x squared minus x squared. So we're going to have delta x squared, excuse me. So these two x squareds will cancel out, leaving us with 2 delta x plus delta x squared divided by delta x, and we're going to factor out the delta x, leaving us with 2x plus delta x divided by delta x. These two will cancel out, leaving us with 2x plus delta x. Now, if we were to using the formal definition, we're going to plug 0 in for delta x, leaving us with 2x. Now, at which point do we want to find the instantaneous rate of change? Let's say that we want to use the point, 2, 4. So we're going to plug in. So since we have 2, 4, we're going to plug it into this function. This function we're going to denote as f prime of x. And plugging in 2, we get 4. That's the slope. Now we want the actual function for the line. We're going to use point slope form. Y minus y1 equals m times x minus x1. So we're going to have y minus 4 here equals 4 times x minus 2. And we're basically just going to simplify that, distribute for x minus 8, leaving us with 4x minus 4, which will be the slope of the tangent line at 2, 4. And with that example, I conclude this video. That's essentially what a derivative is, and I hope that you find this useful. Thank you.